Well, I thought the lighting problem was not a problem. I saw a few streaks. You can still see them now, but not a problem. What was a problem, I thought, was the air conditioning. So this time I've switched it off. So things should be a bit quieter. Alright, well, moving on, we'll do the third example of this coset theory of trying to solve particular problems. This one's fairly similar to the second one, so like as for 2. So again, you have the set of twice differentiable functions. Binary operation is plus, so you're adding functions like f1 plus f2. Okay, so the mapping from this set to this set. So mapping D to itself, so no change, that's the same as 2. But when you're mapping at the level of element, so this F is a member of D, right? Remember D's set of twice differentiable functions, right? So you're mapping this element to this element, and this element here is a member of this set still. Because if f's twice differentiable, then differentiating it once is okay, that's defined, and differentiating it 0 times, also defined. Okay, so the only difference between 3 and 2 is this extra term here. Okay, now proving that mapping, that I'm loath to call it function, confuse things. This mapping, little d, it's homomorphic. I haven't proved it, but I assume it's pretty obvious. Right, so imagine you had little d of f1 plus f2. Well, this is linear, so I'll assume you're quite capable of proving that this d here is homomorphic, right? I won't bother with that. All right. Now the actual problem that you're asked to solve, in other words, find the set of solutions to f here, you find the functions f belonging to big D, so that this is true. So effectively you've got a differential equation. Okay. So as in part 1, part 2, find a little a, like a particular solution, and then find the kernel, and then binary operate little a, binary operation. In this case it'll be plus. With the kernel, so a little circle, big K. Okay, so find a particular solution. So little a for this. Well, I mean, a pretty obvious one is just f is 2, right? If you differentiate 2, you get 0. So f of 2 is a solution. So let that 2 be your little a, from what I was talking about in the theory last time, right? Now how about the kernel? What's the kernel of this mapping, little d? Well, now remember what the definition of kernel is? It's the subset of your group G, your starting group, that all of whose elements map to the unit of your target group, H. Right? So the unit of this. Now what is the unit of this? Now the binary operation is plus, so the unit element will be just 0. Okay. So you want the solutions to this, where there's your unit 0. So what are the solutions to this? Well, if you take f to the other side, you get minus f, and that's the solution's exponential. You'll have something of this form. Okay, so that's your kernel. So little ak, as in the theory before, you've got a binary operation between the little a and the k there, and in this case it'll be plus, because that's the binary operator in this context, right? Plus, right? So your little a is 2 plus, and here's your kernel, right? So there's your general solution. Now, if you're familiar with differential equations, DEs, You've probably heard this, the kernel, this form, referred to as the complementary function. So just a different terminology because you're taking a whole different approach to solving DEs. And your particular, well, your solution, little a here, is usually in the context of DE, differential equation theory, is called a particular integral. All right? Okay, so that's the third and final example of coset theory applied to solving particular type problems. Here was a DE, differential equation type problem. Right, so now somewhat of a new topic. We'll talk about the quotient group of K. Now remember K, the kernel, it's not just a subset, it's a subgroup. We proved that in the previous lecture. And it's not only a subgroup, it's a normal subgroup. Also proved that previous lecture. And you know from previous lecture 2 that if you have a normal subgroup, that means you can use that to create a quotient group of your starting group G. So now look on your kernel as now the means, the way to generate a quotient group. So that's what this topic is about. It's about the quotient group, or the factor group, same thing, of your kernel of K. Right? So what I've just said, written out here, so the kernel K, well, assuming you have a homomorphism, right, between your G and your H, and you map the function f. So you map from your G, your starting group, to H, your target group, right? So assuming that mapping F is a homomorphism, right? Then that kernel, that K, is a normal subgroup, right? And that was the content of theorem 62. Previous lecture, right? So that means your quotient group that you generate, that's a set of cosets of your kernel, comma, and that set of cosets is the quotient group, right? So talking about a group, quotient group, what's the binary operation? Well, I've been calling it last couple of lectures subset multiplication. Right? You take two subsets and you multiply them together using the binary operation of your starting group, your G, big G. Right? Now, let's see. We do example 1 and 2 of the quotient group of the kernel. So there's two examples. Was there a third? Hold on, let me just check. I constantly run out of board. I'm debating whether I should buy an even bigger one. This board's not bad. If I buy a bigger one, then the camera would have to move back a bit more, I guess. And then maybe you wouldn't see the writing. So maybe this size is about right. I mean, this is lecture 19, right? Still experimenting. So it has not been easy. So, no, only two examples. All right. Now, these two you have seen before, not in all details, but certainly the mapping and the starting set and the target set you've seen before in both cases. It's just that the normal subgroup that we're using this time is different. This time it's the kernel. Right? We're talking now in the context of the quotient group of the kernel, big K. Right, so here's, we're mapping the integers, binary operation addition, and we're mapping those integers into this set. Now you've seen this before, so set's just 1, I, minus 1, minus I. Okay? So this would be a many to one mapping. In fact, an infinity to one mapping, right? Because an infinite number of integers map to 1, and an infinite number of integers map to I, and so forth. Okay, so that's the mapping between sets, starting set and target set. Here's the mapping between elements. So little n here is just an integer belonging to this set here, set of integers. Okay, and this element here, it's only 4 different kinds, has the form I to the power n, the integer, right? And this can only take 4 values. If n is an integer, this can only take 4 different values, and here they are. Right? So it makes sense. It's well formed. All right. So what are we trying to do here? Well, we're trying to find the quotient group of the kernel. Okay. So what is the kernel? Well, it's the set. Well, in fact, a subset of integers, such that I to the n equals the unit of h, the unit of this. Just a minute. I couldn't even get the cursor onto the damn button. One of the disadvantages of living in China is it's government policy not to have too efficient a link between China and the US on the internet. The government's had to compromise. On the one hand, they don't want students becoming too influenced by American thinking, media and so on, because that would just hasten the democratic revolution, or maybe even democratic civil war that China has yet to undergo, I'm predicting within a decade. On the other hand, it can't completely cut off contact with the US, because that would be really bad for China's economic, financial and so on development, so they compromise. But the net effect is, for me, living in China, is that everything, when I'm as of this moment, simultaneously, I'm uploading to YouTube, and it's slow, and it drags everything else down. And I couldn't even move my cursor quickly to a button to click something off. Anyway, side issue. All right. So let's find the kernel for this mapping. What is the kernel? Well, first we need to show that the mapping F is a homomorphism. Otherwise, all this theory is not applicable. Well, proving that this function is homomorphic, is that sort of pretty trivial? I mean, I didn't bother with it here. Now you have to show that F. Now the binary operation is plus, so proving F of Mn in fact